Hey everyone, Big Mac here. Welcome to another QualQuest. My voice is still pretty out of whack, so I'm not going to talk much. Here's an linear algebra problem that we had. It's a lot of definitions, so I will go through each of those as needed. So here I just have a few definitions written up, as well as what they mean for our problem. So basically, all those terms mean that we have real positive eigenvalues all between 0 and 1. That's what all that term means at the beginning. Let's write our matrix into diagonalizable form. At least one eigenvalue is 1. So if any eigenvalues are less than 1 to start with, then they're, as we take the limit to infinity, they'll go to 0. So only eigenvalues of 1 at the beginning will remain throughout. And thus we do have a matrix that is non-zero and exists. So now we check to see if it matches our definitions of projector and if it's an orthogonal projector. Again, eigenvalues are 1 if they were 1 to start with, and they're 0 at the end if they were less than 1 at the end, or if they were less than 1 to start with. Okay? So it turns out that it is a projector, and it is orthogonal since it was Hermitian at the beginning. Okay, I've got some extra time on this problem. I kind of went through that one pretty fast, so go ahead and pause back if you want to look at a couple screens. I'm going to do a couple more problems since I've got time. This is the first half of a problem we got involving some partial differential equations. We have a partial differential equation utt equals uxx. So the second derivatives in space and time match up. And we're asked to find that this energy norm is a constant. So how can we figure that out using the fact that we have periodic solutions? Okay, for some reason I can talk a little bit better if my eyes are closed. I don't know why, but maybe I'll try that a little bit. So since we want our e to be a constant, we can show that its derivative is 0, and that will be the same thing. So if we can take the derivative of our energy function, since we're expecting it to be a constant, we can take the derivative on the inside. So we take it on the inside, we just do a basic chain rule. We take 2 times 1/2, which is 1 of our ut times the derivative of that with respect to time. Utt, same for ux, and we have this part. So now what? We make one sneaky substitution into our formula. We plug in uxx back in for utt. So now we have this thing, which is actually the chain rule derivative of utux with respect to x. So then we just evaluate this at the bounds, which we mentioned had periodic conditions. So these are going to be the same value both times. So thus we have 0 by our periodicity, and thus our energy is a constant. For the last problem, I'm going to talk about some operator theory. Basically, we have a function y, and we integrate it with respect to 1 plus x squared plus y squared in the denominator. So we want to show that this operator is bounded such that there's some constant m, such that as we perform the operation on this function, it's within the bounds of m times our function f. So we want to show 1, that it's a bounded operator, and 2, find this kind of upper bound for it. To find an upper bound on our value m for our operator k, we want to find the f function that maximizes this ratio. We're going to take it 2 norms since we know that f is in L2 space. So we take our operator to we take the norm of that, the 2 norm of that, which means, like normally for a 2 norm, we take the thing squared and then square root on the outside, and then we still have f squared on the bottom, or the 2 norm of f on the bottom. So plug everything through. this top is also integrated by dx, and on the inside it's by dy. So let's organize this a little bit more carefully. So in being a little liberal with our organization of terms, we're going to put the dx in on this side, and then we're going to leave the function f by itself on the right side. So we're going to have f squared dy, and of course everything is still in the square root. So, but that is the exact same thing as the 2 norm of f, which is the same thing as on the bottom, so they cancel each other out, which is good. So now we have a double integral dx dy of 1 over 1 plus x squared plus y squared, quantity squared. So since we're integrating both x and y from 0 to infinity, we're only going to worry about the right half, or the upper quadrant of our R2. So let's convert this to polar coordinates, where if you remember dx dy becomes r dr d theta, x squared plus y squared becomes r squared, and since we're just doing the upper quadrant, the upper right quadrant, our theta goes from 0 to 2, and since there is no theta in here, we just pull it out. Do a quick u substitution. This stuff all comes out, and then the integral is pi over 4, so square root of that is our upper bound for m. So that shows that this is a bounded operator. Okay, my voice is gone again, so Big Mac saying later.